Good morning, everybody.
Good morning, Professor.
Good morning.
Okay. All right, let's get started here. Now, I had given you some stuff to do last week, so hopefully you watched some of those videos. I will go over the material from last week again closer to the end, but it shouldn't be too hard. The stuff that was due to be done last week wasn't so bad, I don't think, but some people might have had some issues with it. I did hear from somebody who did say that they had trouble with some of the stuff and wanted some more guidance on it, so we will get some more guidance on that later. All right, let's have a look. So one other thing I want to tell you here is that all of these quizzes are extra credit for this test and for test 4 as well. So anything you do here will be all extra credit. Still worth doing, but it is nonetheless extra credit. Hope everybody understands that. Download. Okay, let's get back to sharing here. Okay. Come on. There we go. All right, so we were dealing with, well, the stuff you would have looked at, hopefully, would have been the stuff to do with work and heat, which actually isn't too bad. And then enthalpy, which isn't that bad either. The bond energies isn't too bad, but the Hess's law is one you might have had some issues with, and that's one I'm going to spend some time on a bit later on. So let's get back on the schedule here, and we'll begin with heat capacity. So we've got this equation here, Q equals mc delta T. I think maybe this week, no, not this week in lab. I think next week in lab you do heat capacity. All right, let me adjust my screen here. Okay. So hopefully, just a reminder, everybody's got their video on here. Olivia, Dorian, you don't seem to. Are you going to? I'm hoping you're going to enable your video here, please. If not, I really want, thank you. And Dorian. All right, well, I'll come back to you, Dorian. If you're not there soon, showing your video, then I might remove you.
Hello.
Dorian? Yeah, I just want to make sure you're on track here.
So
Thanks.
I was trying to get my camera, but it's locked in my brother's room.
Oh, okay. Fair enough. Thank you. Thanks for letting me know.
Yeah, no problem.
Okay. So Q equals mc delta T. That is our equation. M is mass. We've got C, which is heat capacity, and delta T is change in temperature. Switch this around here. So the heat capacity, we'll talk a little bit about that. It's measured in joules per gram per degree Celsius. And what it's defined as is the energy required to raise 1 gram of a certain material by 1 degree Celsius. So that's why the unit there is very important. So it's joules per gram per degree Celsius. And if something is slowing down my computer, I'm hoping that it will speed up in a second. Jeez. Let me see if I can close this down. See if that speeds things up a bit. Okay. Here we go. Magic, isn't it? Okay, joules per gram per degree Celsius. So grams of material, degrees Celsius of material. So per, that's what heat capacity is. So the higher the heat capacity, and water is 4.18. This is for C, 4.18 joules per gram per degree Celsius. And if you've got something like metal, most metals, usually we'll say less than 1 joule per gram per degree Celsius, generally speaking. So what you're finding here is that water can take a whole lot more energy to raise 1 gram 1 degree Celsius, whereas metals have a lot less energy to get 1 gram, to raise 1 gram 1 degree Celsius. So I know a lot of you have heard the saying, watched pot never boils. So it just seems that, you know, when you're watching water boil, it takes ages to seem to have it to boil. And the reason for that is because it's got such a high heat capacity. So for every gram of water you've got in the pot, to raise it 1 degree Celsius, you need to put in 4.18 joules. So if you're trying to raise water that's at, say, 25 degrees up to 100 degrees, it has to go 75 degrees Celsius. And that means it needs 4.18 joules for every one of those degrees Celsius. And then for every gram, it's going to be 4.18 joules as well. So there's a lot of stuff that needs to go in order to raise, a lot of energy needs to go in to raise that temperature of the water to boiling. Metals, on the other hand, if you would have noticed that if you ever stick a spoon or something on a stove, it doesn't take very much to heat it up. It gets hot pretty quickly. And that's because metals have much less heat capacity. It takes much less energy to heat the same amount of metal as it does water. So that's what we notice in real life here. So let's look at an example here. What is the final temperature of a 10.00 gram copper ring that absorbs 45.0 joules of heat? Now, one presupposition here is that we already have the heat capacity of this copper ring, which is 0.385 joules per gram per degree Celsius. So as you can see, that's much less than 1, the 0.385 that we're dealing with there. So let's look at how we deal with a problem like that. So we apply Q equals mc delta T. The Q is always going to be in joules. That's the energy. So what we do is we rearrange our equation here. Delta T equals Q over mc. So what we're looking at, let me make that a Q, make sure it's a Q. There we go. So what we're looking at here is for a change in temperature, which is delta T. So delta T isn't actually just a temperature, a single temperature. It's a change in temperature. And we can rearrange this to get delta T. And you can see by doing that, we've got 45.0 joules for the Q. We've got 10.00 grams for the mass. And then we've got the heat capacity, which wasn't given in the problem, but we assume we had it as 0.385 joules per gram per degree Celsius. So the temperature change was 11.7 degrees. Now, what's really important here is the wording of this problem. It says, what is the final temperature of a 10.00 gram copper ring at 20.0 degrees Celsius? That's the initial temperature. And the key word here is absorbs. So that means that if it's absorbing heat, naturally the temperature is going to go up. How much is it going to go up by? Well, it's going to go up by the delta T that we calculated down here, 11.7 degrees. So there's two possibilities for this kind of problem. It could be the final temperature after it absorbs heat or releases heat. If it releases heat, then it's going to cool down. And what we would do here is subtract. So instead of doing plus here for the 11.7, we do minus for the 11.7, and that would give us the final temperature. Does anybody have any questions about this particular problem? So the key word here, absorbs, and that's why we add, because this is a change in temperature. We're already given the initial temperature as part of the deal here. And then we've got the plus here because it's absorbing, and it would be minus if it was releasing. All right. Now the kind of problem that is a little bit more difficult though is this kind of problem where we take a metal block and it's at a certain temperature. We don't know what that temperature is, the initial temperature. What we do know though is that it's been put into some water, and that water has a certain temperature and a certain mass. And we also know the water's heat capacity as well. And you can see that that's listed here in the problem. So in the problem, we've got the heat capacity of water. We've also got the heat capacity of iron here, which is 0.449 joules per gram per degree Celsius. So the diagram down the bottom shows you what the story is here. So you've seen situations like this before. It's like somebody's making a sword and they put it into a fire, and then it heats up, and then they take the sword and they stick it in the water, and the water steams up. All of that's happening. So, and you know what's happening is that the iron is hot, then the water is cool. So what happens is that the iron will cool down, but also the water will heat up. So this is what we know about this kind of problem. The iron block will release heat to the water, and the water will gain that exact amount of heat. The other assumption we're going to make here is that the final or equilibrium temperature of the water and the iron block are the same. So what we're saying there is that the temperature of the iron block is going to go down. It's going to cool. The temperature of the water is going to go up. They're going to kind of meet in the middle, and at some point, the temperature of both the iron block and the water will be the same. I think that makes sense. Does anybody have any questions so far? Okay. So how do we deal with this kind of problem then? Well, when we're looking at this kind of problem, we've got to figure out what we have to find first. And in this instance, we're looking for the initial temperature of the block, which is here, initial temperature of the block. So if we can't really start with the iron or anything to do with the iron, we've got to be starting to do something with the water first. So what we want to find here is the amount of heat that was absorbed by the water. What you'll notice is that the water was initially at 20.00 degrees Celsius, and then at equilibrium, that is after some time has passed, the temperature of the water was 22.00 degrees Celsius. So the water went up by 2.00 degrees. You can see that that's a difference between the 22.00 and the 20.00. So it went up. What that means is that the temperature of the block must have gone down. And I think that's important to realize as well. So because the water went up, we know the iron must be going down in temperature. Because what happened was when the iron was put into the water, it released heat. And that's what caused the water to go up in temperature. Does anybody have any questions so far? So our first mission here is to find out how much heat the water actually absorbed. So we're using our equation here, Q equals mc delta T. So Q of water, so that's the heat absorbed by the water, is the heat capacity of the water, which we were given, 4.180 joules per gram per degree Celsius. The mass of the water was also given, 100.0 grams. And then we've also got the delta T of the water. That's the change in temperature. That's 2.00 degrees Celsius. Notice I'm not really that interested in signs here, negative or positive. I'm really just interested in how much or quantities, and we'll figure out what's going on with the signs a bit later. So it turns out that would be 836 joules once we do the math on that. But this also means that that's the heat released by the iron into the water. Does anybody have any questions so far? So if you remember, we're looking for the initial temperature of the ion. So to do that, we need to find the change in temperature of the ion. If we know what the heat given out by the ion was, which was 836 joules, then we can solve for delta T, knowing what the mass and the heat capacity of the ion is as well. All of that was given in the problem. The mass of the ion and the heat capacity of the ion are given to us. And you can see the change in temperature of the ion was 124 degrees Celsius. This does not represent the initial temperature of the ion. It represents the temperature change for the ion. Now, what this means is we know that at equilibrium, it was 22.00 degrees Celsius. That means that at the point of equilibrium, the temperature of the water was 22.00 degrees, but so was the temperature of the ion. So this would be the final temperature of the ion. What we need to do, though, is figure out the initial temperature of the block. Now, we've already established that since the temperature of the water went up, the temperature of the ion must have gone down, which means the initial temperature would be 22.0 degrees Celsius plus 124 degrees Celsius. That was the temperature change of the ion. So the initial temperature would have been 146 and it went down to 22. Does anybody have any questions? Does anybody have any questions? Okay, so let's look at some problems here, and I will get you to focus here. Sorry, my mouse is not being very friendly with me right now. Here we go. So you'll notice that along with the videos here, these were the ones I gave you links to. I know that initially the links might not have worked in the email, but I told you they were also linked through the mini lectures as well. So these links actually work. Also, I did change the ones in the syllabus so that they worked properly as well. So you shouldn't have had any trouble getting to those videos. So these were the ones I wanted you to look at last week. And you can see that you've got some quizzes here to do. These are extra credit, as I had said. So they're good practice. We've got the Hess law ones as well. And I've got a worksheet here. And that's what I'll go over when we are closer to the end here to review on the Hess law, just in case anybody didn't really get that very well. Down here, we've got the heat capacities quizzes. And what I want to do is do a couple of these problems from the practice quiz here, which is similar to, or at least some of them are similar to what you're going to see on the real test as well. So let's take a squiz at the quiz. A squiz is a look, by the way. It's an Australian word. Take a squiz. Okay. Right. Now, so this problem we just did is very similar to what we just did. We're looking for the initial temperature of the tin rod. Now, this one is a little bit different. And this is the other kind of question you've got to be prepared for here. And that is looking for the initial temperature of the water. So you can see there it says water is the initial temperature. So let's take a look at the problem set up here. So we've got a tin rod and it's going into water. Now the water we know the tin rod is 200.0 grams. We also know the initial temperature, it's 178, let me use this slash here, 178.0 degrees Celsius. We know that. We know that the final temperature of the water is going to be 30.5 degrees Celsius. But that also happens to be the final temperature of the block as well. So that's important to note. And what we don't know is the initial temperature of the water. We do know its mass, though, which is 100.0 grams. But we don't know, so this is initial, this is final. What we don't know is what the temperature of the water is, and that's what we're looking for, the initial temperature. Now, what we know is this. We know that the tin went down in temperature. Now, how do I know that? Well, it started out at 178.0 and then it was 30.5 degrees Celsius. So it did go down in temperature. What that means is the water must have gone up in temperature. So we know the water at the end is 30.5. The point I'm trying to make here is that the temperature of the water must have been less than that initially. That's the point I want you to all to understand this right now. That the water must have been less than this initially. Does anybody have any questions? Nobody has any questions. Everybody's fine with that, huh?
So what are we going to do for the final answer?
I'm sorry?
For the final answer, what will it be?
We'll see in a second.
All right.
I'm just, Michael, I was just trying to lay the groundwork here a little bit, lay a bit of foundation before I started into the problem. But are you okay with what I've said so far, Michael?
Yeah.
Okay, good. That's good. I think a lot of it does make sense, at least from an intuitive point of view, which is good. Okay, so we're going to work first of all with the tin because we know all the information about the tin. We know the mass of tin. We know the heat capacity of tin. It's given in the problem. And we also know the change in temperature of the tin. And we're going to figure out the heat of the tin, or the heat released by the tin. So we've got 200.0 grams. We've got the heat capacity of 10.210 degrees Celsius, sorry, joules per gram per degree Celsius. And then we've got the change in temperature. Now the change in temperature is going to be 178.0 minus 30.5 degrees Celsius and let's work that out a little bit here. So it'd be 178 minus 30.5 and we get 147.5, which is correct for significant figures. That's the temperature change of the tin. Anybody got any questions so far? All right, so let's look at what the final amount, well, it's not really final, but it's the amount of heat released by the tin. 200 times 0.210. And then, let's see, 147.5. Okay, so 6195, or we'll say 6200 if we're going to go to sig figs here. My recommendation, though, would be for these problems here, just use all the significant figures. I think I've got answers for both instances here, so I don't think it's going to matter too much. All right, the next thing we need to do is figure out the change in temperature of the water, and the delta T of the water is going to be the Q of the water divided by the mass of the water times the heat capacity of the water. But the heat released by the tin is the same as going to be the same as the heat gained by the water, which is 6200 joules or 6195 joules. I'll go ahead and use 6195. And the mass here is, let's see how much, 100.0 grams. And we've got the heat capacity, 4.18 joules per gram per degree Celsius. Now the answer there 6195 divided by 100 divided by 4.18. So what I've done there is I've just divided anything that's on the bottom. Okay, so that comes out to be 14.8 degrees. Now this isn't the temperature of the water. What this is a change in temperature of the water. So I had said this earlier, that we knew that the final temperature of the water was 30.5 and that the temperature of the water must have gone up, which means the final temperature of the water is actually going to be 30.5 degrees Celsius minus 14.8 degrees Celsius. And that would be 15.7 degrees Celsius. So that would end up being the initial temperature of the water. So it was initially a lot less. All right, does anybody have any questions? So you'll notice a difference in this problem relative to the one that we first looked at, where we were looking for the initial change in the metal. Because to get the initial change in the metal, look what we did. Let's go back to that. You'll see that what we did was we added at the end, right? You see that? We added. And then for the water, we subtracted, right? So it's a matter of what's going on in the problem to decide if you add or subtract. Depends on what you're looking for. Does anybody have any questions about these kinds of problems? So my recommendation is that you do two things here. You do the heat capacities quiz, the practice quiz and the credit quiz. And also, in addition to that, let me get out of here. Also, I recommend that you do the quizzes. Sorry, let's go back to this. See if I can get this mouse to work a little bit better here. Let's try a different port, see if that helps. Give me a second. Let's see if that's any better. Okay. Okay, that's better. All right. So go back to test 3 and the practice quiz. Practice quiz here. Practice test 3 ungraded. Let me show you what the questions look like for that. So additionally, for the other ones, the ones that I was sort of directed you to do last week, you really should have been into practicing these as well. Now remember, even if you didn't really understand how to do this kind of problem here, question 2. I do have videos for that should have helped you with being able to do that kind of problem. The Hess's law ones, I know those are a bit more of a challenge. I will go through some of those in more detail a bit later. All right, let's go back to the heat capacity problems. So these are the heat capacity. You see, I do give you the equation here as within the test. And there you go. You got these kinds of questions that I had just been going through. All right, so one here that looks for the temperature, the initial temperature of water. This one here is also the initial temperature of water. It's random. You never know what you're going to get with these. So yeah, you're going to get 2 problems related. It could be the same thing, could be completely different. I don't know. I mean, this one's about initial temperature of water. You could be getting initial temperature of the metal as well. All right, does anybody have any questions? Okay, those aren't too bad. I strongly recommend practicing those. Okay, let's continue on here. A related concept here is stoichiometric enthalpy. So we're given a reaction here that has a certain enthalpy. This is something we had talked about. Well, something I dealt with last week in the videos. So we've got a delta H value here along with a chemical reaction. So what that tells you is that chemical reaction with that specific stoichiometry, so the stoichiometry relating to the coefficients, whatever's in front of each of those things there, you know, the 2, the 3, the 2, and the 4. So those coefficients, the numbers out the front of each of those compounds. And for that specific reaction, we have a delta H of negative 790.3 kilojoules. So what does that mean? What it means is for that specific reaction with that specific stoichiometry, the heat released was 790.3 kilojoules. And the reason I know it's released is because it's negative. If it was positive, then I would have said the heat was absorbed. So we call this an exothermic process. So again, if this is not something you're familiar with, you can go back, you can look at those videos I asked you to look at last week. And I go through the concepts of exothermic and endothermic. But the point is that this is the amount of energy that's released by this equation with this specific stoichiometry. So 2 moles of methanol, 3 moles of oxygen gas will give 2 moles of CO2, 4 moles of water, as well as releasing this much heat as well, 790.3 kilojoules. So this is methanol, which is an alcohol, and it will burn and it will release heat. Methanol is used sometimes as a fuel as well. So what we're looking at here is what mass in grams of methanol must be burned in excess O2 to liberate a certain amount of energy. So we know how much energy, say 2 moles of methanol will generate, and it will be 790.3 kilojoules. So this just involves a bit of dimensional analysis. So we start out with 8.00 times 10 to the 6 joules of energy, which I've written here as 8.00 E6 joules. I convert that to kilojoules because my delta H is in kilojoules. So that's the first thing. The next one is the kind of the important relationship here. We've got 2 moles of methanol to create 790.3 kilojoules. And that's why I've put the kilojoules on the bottom to cancel the kilojoules on the top over here. And the 2 moles, of course, goes on top, and 2 moles creates that much energy. Now your question might be, well, where'd the negative sign go? Why didn't I include the negative sign? Well, it's really about the wording of the problem. It's looking for a mass, and that mass is not going to be a negative mass. It's going to be a positive mass. That's the mass that actually gets burned. If you wanted it to be negative, then you could say, well, you could argue, and if it was negative, well, that's the amount we lost. But that's not really what it's asking. It's really asking what mass must be burned. So that really should be a positive value. That's why I've ignored the negative sign here. Then in order to get to grams, I put moles of methanol on the bottom and then the molecular weight of methanol on the top. We do the math, it comes out to be 649 grams. Does anybody have any questions about this first example? So what we can also do is we can do the reverse of this problem as well. What energy in joules is released by 50.0 grams of methanol? So we know what the molecular weight is because we can add it all up. It's actually given to us in the problem as well. But the first thing we want to do is figure out how many moles of methanol we're starting with. And that's why we've got 50.0 grams of methanol times 1 mole of methanol over 32.05 grams of methanol. We're looking for energy at the end, so we're still going to use this same relationship, but now it's flipped. The 790.3 kilojoules will be on top and the 2 moles of methanol will be on the bottom. But again, you'll notice that the moles of methanol will cancel, which is what we want to have happen. We need joules at the end, so we do times 1000 joules over a kilojoule. So you can see these problems are just the reverse of each other really, and that gives us a final answer of 6.16 times 10 to the 5th joules. Does anybody have any questions?
How did you get the 790 kilojoules?
It's given to you in the problem here. Do you see it's with the reaction? And it always will be given to you with the reaction.
Oh, I didn't even see it right there.
Yeah.
Okay, thank you.
So 2 moles of methanol, that's where the 2 moles comes in, and the 790.3 comes from here. Is that all right, Joseph?
Yeah, that's good. Thank you. Sorry, I didn't even see the 790 over there.
Okay. All right, let's have a look. Hang on. Go back to, excuse me. Oops, wrong link. So let's look at the same problems in practice test 3. They're actually very similar to the ones in the PowerPoint. There's a quiz for it as well, an extra credit quiz that you can do. I'd recommend doing that as well. And there it is. Now, I know you might be saying, well, you don't know what a megajoule is, you don't know how to deal with this problem, but you can always watch the videos for these specific problems, and that's what I'd recommend doing. But we're looking here for the megajoules instead of kilojoules, and you'll see that all you really have to do is get to joules at the end, and then you can convert it to megajoules. And I have given you a conversion factor here and to make you get to that point. So the same kind of thing. All right, so again, you can, if you have any problems with the wording, you can always go look at the videos for these specific problems from the practice test. Does anybody have any questions? All right, let me show you those videos just in case you haven't seen them yet. I really can't have been any more transparent about any of this. If you put the work in, you'll do fine. The people who fail this test are the people who wait until the very last minute and don't do the practice test at all. But there's your practice test 3 videos. You'll notice there are 17 questions. I have a video for each of them. In the case of question 2, I've actually got 2 videos, depending on which case it's dealing with. So I would very strongly recommend watching those videos if you're having any trouble with the wording of any of those problems that's in the practice test. Let me show you also the Stoichiometric Enthalpy folder. And again, you have a quiz, a practice quiz, and you need to get 80% on the practice quiz to open the credit quiz. You get 2 attempts at the credit quiz, and that's extra credit. Does anybody have any questions? Okay, that's good. All right, let's get a start here on the Bohr atom and the kind of problem you're going to have to deal with here. So I'm going to give you a little bit of background first about what's going on. First of all, let's talk a little bit about light. And generally speaking, when we talk about light, it's viewed as a very small particle called a photon that travels as a wave. Now, waves have 2 characteristics. We can talk about wavelength, which, as the name suggests, is a length, and it's usually presented in meters. The other one that's difficult to show on a static diagram is frequency, which is measured in hertz, Hz, or seconds to the -1, or cycles per second. Frequency is defined as how many of these peaks or how many of these tops of these waves go past a certain point in 1 second. So high frequency means lots of these are passing a certain point in 1 second. Let me see if I can show you a video of a frequency. Let's have a look. Let's have a look. I don't think I'll use that one. Let's have a look. Let's have a look. Okay, yeah, this is a good one. So this is low frequency, and you can see that what's important, let me play the animation on this one too. And this one's high frequency. Now what's important here is these waves are traveling at the same speed. But what you'll notice in the case of the low frequency, if we're just taking this point here, fewer of the tips of the peaks go past this point in 1 second. So what you're seeing here is the relationship between frequency and wavelength. So what I'm saying is this is long wavelength. Let's stop this. This is the wavelength right here between the 2 humps, and in the bottom one here you can see the wavelength. So this is long wavelength, this is short wavelength. But long wavelength means low frequency and short wavelength means high frequency. The important point being that these travel at the same speed. So what speed do they travel? Well, they travel at the speed of light, which is a constant value of 2.00 times 10 to the 8th meters per second. Obviously, these aren't traveling at that speed, but the whole point is that you can see the relationship there between frequency and wavelength. So cycles per second. So it's the number of of these waves that pass a given point in 1 second. That's frequency. Does anybody have any questions? All right. So let's apply this now. Let's look at the relationship between them. And it is nu equals c lambda. Okay, so nu is the frequency. Which is in hertz, or seconds to the -1. And then we've got lambda, which is the wavelength. Which is measured in meters. And then we've got c, which is the speed of light, a constant value, of 2.00 times 10 to the 8th meters per second. So you'll notice that if you have meters per second, I think I might have, sorry, I screwed up the equation there. Doesn't make any sense. Let's try that again. I had a brain freeze. Let's try that. C equals nu lambda. That's what it is. That's seconds to the -1. That's meters. That's the wavelength. And this is the speed of light. Sorry about that. And that's in meters per second. So you can see how the units work out there. Meters, seconds to the -1. Hertz is the other way that you could express that. It's the same thing. Frequency. And this is wavelength. Okay. And you can see you can sort of see the relationship between them. You can see that lambda would equal c over nu. So that you see that's an inverse relationship. And that's what I was talking about earlier. As one goes up, the other one goes down. Okay, does anybody have any questions? All right, well, let's look at how we might apply that then. And we're going to apply this to what goes on with a hydrogen nucleus. So this in a hydrogen atom, and I'm just going to use a very simplistic model here. So there's your nucleus, which is just a proton, and this is an electron that is going around the hydrogen atom. Now, we know that this is not really the way that this actually goes, and I'm going to show you pretty soon with regard to some quantum mechanics exactly what's going on with this electron, but this is just a very rough idea of its energy. And in its ground state, this electron is said to be at the energy level where n equals 1, which represents this circle around where the nucleus resides. Now, there are other energy levels around this, and it goes infinite. It's an infinite number of these. And what can happen is that we can put energy in, and the electron can go, let's say, out to here, maybe out to, say, n equals, this would be 1, 2, 3, 4. And we can excite this electron and put it into the n equals 4 energy level. Then what can happen is that this electron can then, it can fall back to any of these other energy levels. But the trick is And this is why it's called quantum. The trick is that the electron can't stop in between the energy levels. It's very specific. It can only stop at the energy levels themselves. So when this electron falls back down, it releases a photon that has a certain wavelength and frequency. And we can actually calculate that based on the difference between these energy levels. So that's the nuts and bolts of it. Let me see if I can for orbit energy. See. And let me see if I can find the right. Here we go. All right. So this is a good, I like this one here. So what I'm suggesting here is that an electron has been sent out to n equals 4. And you can see that when that electron, sorry, n equals 5, when that electron comes back down to, say, n equals 2, then it releases a photon that actually is violet in color. And that's because of its frequency and its wavelength. The one that goes from n equals 4 down to n equals 2 would be blue and green, or blue-green. And the one that goes from n equals 3 down to n equals 2 would be red. And we can actually calculate these frequencies and wavelengths based on equations that I'm going to give you here. So you can see the colors of these different lines here from the spectrum. And this can actually be made visible by a spectrometer, or a device that we can actually see these colors of these lines here. So that's what it says by quantized energy states. It means that simply that the electron can't stop in between. It has to go down to these specific energy levels. It can't stop in between them. So that's what's called quantized. So let's look at the kinds of question, or the kind of question you're going to need to be able to answer here. So it says, what is the energy, wavelength, and frequency of the line of a spectrum of hydrogen that represents movement of an electron from a Bohr orbit? It'll always be something big to something smaller. This one is n equals 6 down to n equals 4. So to get the energy, we're going to use a certain equation. It's called the Ryberg equation. This is given to you. You don't have to memorize it. You'll see it in the actual test as well. I don't make you memorize this. E equals 2.179 times 10 to the negative 18 joules. 1 over n1 squared minus 1 over n2 squared. So the n1 and the n2 are given to you in the problem, n equals 6 and n equals 4. So it's just a matter of plug and chug, really. But you want the energy here to be a positive value. So in order to make that happen, what we would do is we do 1 over 4 squared minus 1 over 6 squared. And you can see that by doing that, we'd do 1 over 16, which is bigger than 1 over 36. So by subtracting these two values, we end up getting what we want as a positive value. So we do the math there, and it comes out to be 7.566 times 10 to the negative 21 joules. Sorry, 10 to the negative 20 joules is what I should say. But you can see that we're asked to give an answer in kilojoules. So there's one other step that I do here. So 1 times 1 kilojoule over 1,000 joules. And that gives us our final answer in kilojoules, 7.66 times 10 to the negative 23 kilojoules. Does anybody have any questions? So we're also asked to get the frequency. Now, energy is equal to h nu. Nu here is the frequency. Let me start that up the top here. And then we've got the energy as well. That's actually what we're given. We found it already. And h here is called Planck's constant. This is something you would be given a value for, along with a unit. And the value is 6.6 26 times 10 to the negative 34. It's a pretty small number. And it's joule seconds. That's the unit, joule seconds. So what we need to do here is now we need to rearrange this, and we do nu equals E over H. Now the E is what we just calculated, 7.566 times 10 to the negative 20 joules. Now I know we've got kilojoules down here, but look at what H is. And this is why I advocate using units a lot, is in joule seconds. So that means the joules will cancel. So notice that I've used the joule value and not the kilojoule value to get the energy in here. You'll notice that the final unit there will be seconds to -1 because it's 1 over seconds. And that comes out to be 1.142 times 10 to the 14. Now I want to stop right here for a second, and I want you to do this calculation in your calculator, please. So I'm going to stop right here for a second. I want you to do that calculation in your calculator. I'll be back in a minute. Some of you, I imagine, didn't do so well with that exercise. You ended up with something like 10 to the negative 54. And that would have been because of the way you put it into your calculator. Did anybody not get the answer that I have here?
I did. I got 1.20.
1.20.
Oh no, I think I did that one wrong. Sorry.
All right. Did anybody not get the 10 to the 14? All right. Well, then I can only assume that you all must have entered it into your calculator the correct way. So just giving a little bit of a thing here. So you would have hopefully used the EE button or the EXP button on your calculator. So you would have put 7.566 EE or EXP and then negative 20 and then divided by 6.626 EE negative 34. If you do it any other way, I think you're going to end up possibly getting the wrong answer. So you're looking for a pretty big number for the frequency, something in the 10 to the 14 range. 10 to the 13, 10 to the 14, 10 to the 15, something like that. Any questions? Okay. The last thing we need to do then is get the wavelength. Now the wavelength needs to be in nanometers. So the frequency was in hertz, which was the same as seconds to the -1. And now we're going to look at how we can get this wavelength here. Now the equation we're using is the one that I mentioned earlier. I screwed it up first, but then corrected it. And that is C equals nu lambda. And lambda is what we're looking for, C over nu. Now C is going to be the speed of light, 2.998 times 10 to the 8th meters per second, over 1.142 times 10 to the 14 hertz, which is also seconds to the -1. So you can see that those will cancel, and we're just left with meters here, which is going to be, well, let me, I think it would be, all right, let's just do the math on that. I want to make sure I get this value correct. And you can see that would be 2.625 times 10 to the, let's see, 1, 2, 3, 4, 5, 6. Let's see, start it again. 1, 2, 3, 4, 5, 6. So 10 to the -6 meters. But we don't need this in meters. We need it in nanometers, and 1 nanometer is 10 to the -9 meters. Now, if we do this conversion, we'll end up with something that is going to be in the hundreds or thousands. In this case, it's in the thousands. And that gives us 2625 nanometers. So you're always expecting something nice to work with at the end here that looks like a number in the hundreds or in the thousands. Does anybody have any questions? Okay, so let's look at some of these resources I have here. I've got the Bohr transitions quiz. I actually also have a video for the practice quiz question relating to the Lyman series. So I do have an explanation for that. So once you do the practice quiz, just look at this video as well, just to get some more clarification about what's meant by Lyman series. And you'll see I've also given you some extra information here about what these series are called here. Now the series themselves, just to give you a very basic idea, I sort of covered this a little bit earlier, but if you've got a hydrogen atom, it's not being very kind here. That's better. But then we've got n equals 1, n equals 2, n equals 3, n equals 4. And if we've got the, we'll do one more here, we'll do n equals 5 as well. And if we're talking about transitions of an electron, the Lyman series represents everything going back down to n equals 1. So from n equals 5 to n equals 1, n equals 4 to n equals 1, n equals 3 to n equals 1, and n equals 2 down to n equals 1. And all these represent different wavelengths of light, and they represent a series because they all end up in the same place. So depending on where they end up, that's the name of the series. So n equals 1 is Lyman, n equals 2 is Balmer, n equals 3 is Passion, n equals 4 is Brackett, and n equals 5 is Fund. And these are named after the people who actually came up with these series or initially saw them. Does anybody have any questions? Like I said, watch the video here. That will help as well. So that's extra credit, as I had already mentioned. Let's go back to test 3 here. Let's see if I can find the problems that relate to that. Here we go. So we've got the equations that you need here. They're all given to you as part of the test. And then I've got this here as the energy in zetajoules. So that's, and I know you might not be familiar with what a zetajoule is, but I have given you a conversion for it here. And if you want more guidance on how to do the calculation, then look at the video that relates to it, the question 4 video for the quiz. If you're not sure how to use this conversion, it'll show you. For this one here, we're looking at nanometers again for the wavelength. And for this one here, we've got the frequency, and that's in terahertz. But again, I'll give you the terahertz conversion here as well. So doing those is not that difficult. It's really not that bad, especially since I give you the equations up here. All right, does anybody have any questions? Anything at all? All right, let's look at the timing of what we're doing here, just so you can be aware of what's going on. So you can see that test 3 will be due on April 5th, right? So that would be, well, let's see, so the 29th. So they were looking at, let's see, the 29th, that would be next Monday. And the 5th, I guess that would be the following Monday. So we're looking at 2 weeks here. We have plenty of time to get through this and to also go back and for me to give you a little bit of a primer on the Hess's law. So I will give you some time to do that. These aren't too bad. The heat and work, the enthalpy, and the estimating delta H by bond energies. If you want some extra help with that, you can always make an appointment with me as well. But I definitely will be going over examples of each of these before the end as well, just to make sure that you don't end up being left behind with that. But you still should have watched the videos for those last week. Now all these videos, I did fix the links here. Initially the links weren't working properly, but I did fix them all, and now they're all link directly to YouTube and not to somewhere else in the course, which is what the problem was. All right, does anybody have any questions about timing or what we're doing or anything else? Okay, well, we'll leave it there for today then, and I will catch you all on Wednesday.
Professor, see you in the lab.
Right,
See you
see you.
later.
No worries, bye-bye.